Continuation. This is a continuation of our 7-1 notes on exponential growth and decay, and we're going to look at some graphs today. So first we want to tell whether the function shows growth or decay. And I can look at the 1.5, the base and the exponential variable is right here, and so I know that this is growth. My multiplier is 1.5. That 1.5 comes from 150%. And what that means is something was growing at a rate, growth of 50%. Because 150% comes from 100%, what we started with, plus another 50%. And so I can look at this and I can pull that apart. Now we're going to graph this without a graphing calculator. If you had a graphing calculator or an online program, you would just type this in and it will put the graph in for you. We're going to go ahead and we're going to use a table, and it's always good to try a couple negatives and a couple positives. So you're going to type into your calculator 1.5 to the power of -2. Now I want to remind you that 1.5 is the same as a fraction of 3/2. And if I take the number 3/2 to the power of -2, the negative exponent flips it to make it 2/3. And then we would distribute the power and we would get 4/9. That should be the same thing we get when we put in the calculator. So when we put this in the calculator, we are going to take 1.5 to the power of -2. And we get out 0.4 repeating. If I take 4 divided by 9, the fraction I got down here, we get 0.4 repeating. Okay, so we're going to go ahead and continue to put our powers in the calculator, 1.5 to the -1, and we will get a decimal of 0.7. Again, we can always use our fractions. 0.7 is really that 0.6 repeating from 2/3. All right, put in 0, we'll get out 1. Put in 1, and we'll get 1.5. So again, we're just putting these in the calculator, and I'm rounding to the nearest tenth. 3 gives me 3.4, and 4 gives me 5.1. So we're going to go ahead and just do a quick sketch of our graph. So I'm going to go to -2 and 0.4, which is about halfway, and we're going to go to -1, 0.7, getting closer to 1, and 0, 1, 1, 1.5, 2, 2.3, 3 gives me 3.4. We can see that it's starting to take off. Do you see how there were small jumps and now it's starting to take off vertically? So we're going to go ahead and sketch in our graph, and we would guess this trend would keep going. If I wanted a little more accuracy, I would keep continuing the x values. And if I wanted to see what was going to happen here, I would continue putting in negative numbers. So just to show you, we're never going to get 0. If I take my calculator and I take 1.5 to the power of -10, I'm going to get a small decimal, 0.017. If I go back and I take it to the power of -20, I'm going to get an even smaller decimal, and we can see that we're getting closer and closer to 0, but we will never cross where y equals 0. So this graph will come in and just hover above the y-axis. This is going to be an asymptote, which means the graph will approach it, but it will never cross it. All right, and that's all we want to do is graph it. All right, we have another function, and it is g of x equals 10 times 0.8 to the x. This is my multiplier because that's what the power is on, so I know that this is decay. Now, when we talk about decay, the 0.8 is what is left. All right, so I know it's decay because it's 0.8. It's less than 1. Between 0 and 1, we have decay. When we have this 0.8, it's what's left, what's remaining. So I know that this 0.8 was out of 100%. So if I go back, that meant the decay was 20%. Because if I take 100 minus 20, I get 80%. And that is my multiplier. So the decay is not decaying by 0.8. The decay was 0.2 or 20%. The 10, that is my initial amount. So initial amount, multiplier, power of time. So again, I want to graph this function, and I have nothing So I'm going to come in and make a t-chart any way you want to, horizontally or vertically, and I'm just going to grab some negative numbers. I'm going to try -4 and -2, 0, 2, and 4. So I'm skipping around a little bit, and if I wanted to, I can always come back and add in more. All right, so using my calculator, I'm going to plug this in, 10 times 0.8 to the power of, and I think it's just a good habit to use parentheses. We want to make sure that the calculator knows to do the power first. And I'm going to put in my -4. All right, that gives me a large number that's too big for my graph, but I'm going to go ahead and keep that. I'm going to just arrow back up and change out my 4 with the 2. That gives me something that is still too big for my graph. All right, let's come in and put 0 in. I get 10. All right, still a little big for my graph, so let's see what happens when we put 2 in here. I get 6.4. Okay, so we know where this is coming from. Go ahead in and put a 4. I get 4.1. And I'm going to go ahead and jump to 6, just so I get a better idea what's happening. And I get 2.6. And just to see where it really goes, let's put in a higher number like 10. Okay, I'm starting to get closer and closer to 0. If I come in and I really jump to 20, you can see if I put 20 in, again, I'm getting closer and closer to 0. All right, so that gives me a good idea of what my graph is doing. So I'm going to go ahead and sketch a quick graph. And so -4, 24.4, that's going to be way up here off of my graph. -2, 15.6, that's going to be off my graph. 0, 10, that's going to be up here. 2, 6.4, that is going to be a little bit off my graph. So I need a better graph here. 4, 4.1 is going to be about here. And 6, 2.6, right in here. And if I extend my graph, 5, 6, 7, 8, 9, here's 10, we would be at 10, 1.07. So we can see that this graph is coming in from up here, and it's coming down. As it comes down, it is going to get closer and closer to 0, but it's going to take a while to do that. So that's a good sketch of my graph. Continuing with our last couple of examples in our 7.1 notes on exponential growth and decay, we're going to do some predictions. So we have a rare Gibson guitar, and it was purchased in the year 2000 for $12,000. All right. Experts estimate its value increased by 14% per year. And we're going to use a graph to find where when the value of the guitar will be $60,000. All right, at this point, we could make a graph, or we could use the graphing function in a calculator or an online site to help us. I'm actually just going to make a table of values as you would to create your own graph, or that you could find in a graphing calculator, or that you would look at on a graph. So we're going to go ahead and just use a table of values for our point. Table of values we're going to create to make our prediction. So we're going to go ahead and set up our function. We have an initial amount of $12,000, and we want to have this amount over time. So the value over time is going to be $12,000, and our multiplier is going to be 1.14. Again, that comes from 100% value of the guitar plus another 14%. That gives us a total of 114%, which turns into decimal 1.14. All right, and then we have it to the power of time, and time stands for each year. So T equals number of years. So if I was putting this in a calculator that graphs, or in an online program, I would just type this in. Y equals 12,000 times 1.14 to the power of X, or T, whatever I'm using there. But without using a graphing calculator, we can still do predictions. Now this is going to take a little more effort. Eventually, as we work in this chapter, we're going to learn about logarithms and how to solve for an unknown exponent given amount. So we really want this to be 60,000 equals 12,000 times 1.14 to the power of t. But I can solve this and get close to it. by using a table value. So I'm going to go ahead and make an XY chart here, okay, or in my case T and Y, which is the same as A of T. And I'm going to go ahead, and I know in year 0 that my guitar is going to still be worth $12,000, okay? So I'm going to go ahead and jump a couple of times. So I'm going to try 5 years, 10 years, 15 years. I'm going to go ahead and jump and just see where I'm at. So I'm going to go ahead and just a basic calculator here, and I am going to type in my values. So I'm going to type in my equation, 12,000, double check your numbers, times 1.14 to the power of 5. And the reason I know that power of 0 gives me 12,000, 1.14 to the power of 0 is 1, and 1 times 12,000 comes back to me. So I'm going to go and put it to the power of 5, and I get $23,104.97. Okay, so it definitely jumped. So let's go and try it for 10 years. Just going to go back up and change this out to a 10. And I get $44,486.66. So I'm going to go ahead and try it to 15 years. We're getting closer. And I am over. So I am at $85,655.26. So I'm going to come into this now. I know that my answer is between 10 and 15. So I'm going to go ahead and try 12. I'm going to put 12 in here. Come down here and put 12 in. And I get 57,814. Now my goal was to get 60,000. So I am below 60,000 at year 12. So I'm going to go ahead and try year 13 and see what I get. So I'm just guessing and checking until I zoom in on this. And at 13 years, I get $65,908.94. Okay, so in year 12, we are under 60,000. In year 13, we are over it. So this guitar will be worth $60,000 somewhere between year 12 and 13. But if I say it happens in 12 years, that is not quite 60,000. So find a graph for when the value of the guitar will be 60,000. That's going to happen in 13 years. 13 years, value of guitar will be over 60,000, okay, dollars. So if the guitar was bought in the year 2000, then that would be the year 2013. That's the year we can expect the guitar to be worth over $60,000. All right, so we have a depreciation one. Before I move on to that, again, I would graph this, and on my graph, we would see that my graph would start, we'd have it charted out here, but it would start at 12,000, and then my graph would start going up. And so we would have our time down here, and we would have the value over here. And so if I was looking at my graph, I would count up to 60,000 and see where it hits and come down and see what that time is on the x-axis. But I was able to do that by trying some numbers, and I knew it was between 10 and 15, so I zoomed in and checked on those. Okay, so back to this depreciation example. We have a truck for $28,000, and it decreases 9.5% per year. Write an exponential function and then graph the function. Use the graph to predict when it will fall to 5,000. We are not going to use a graph. We are going to use a table of values. But again, if you're using a graph, you would have your years or time on the x-axis, and you would have the value on the y-axis, and your value here would start at 28,000, but this time it is going to come down over time. Okay, so we'd want to know when it hits 5,000, and we would look for that time. That's how you're going to read a graph. We're going to go ahead and write our equation. It's 28,000 times my multiplier. Now, I'm starting with 100% of the value and losing 9.5%. So when it's decay, we want to take that away. it's good to double check your numbers. So we're taking 100 minus 9.5, and that gives me a decimal of 90.5%. Sorry, it gives me a percent. And I'm going to change that to decimal 0.905. So really watch how you write this, 0.905. If I was losing 9%, I'd have 0.91. So this does make sense to the power of time, and T stands for number of years. You want to watch if it's years or decades or months. Okay, so we're going to go ahead and make a chart again. And I know if I put 0 in, 28,000 times this to the power of 0 will give me back 28,000. And then I need to start with some numbers. So I'm going to go ahead and do a 5, 10, 15, and we'll see where we get with that. So let's clear out our old information, type in our function times 0.905, you can read it right there, to the power of 5. So in 5 years, this value of the truck is about 17,000, so 16,998. We're going to round to the nearest dollar. So I'm going to come back up. I'm going to change that out with a power of 10. And that gives me $10,319. Come back in. Let's go 15 years. We're getting closer. Okay, so I'm at $6,264, 265 if we're rounding. I'm going to go ahead and jump to 20 years. What's happening is the process of decay is now slowing down, okay? As my graph comes down, it starts leveling out. So it's not going to jump. So the first 5 years, we have the biggest jump. It's about $1,100. And then the next time, we have a jump of 7,000. And now we have a jump around 4,000. So you can see that we're decreasing by smaller amounts. So I'm going to go ahead and try 20. And 20 gives me 3,800. So 3,803. So I know that my answer is between 15 and 20 years. So I'm going to go ahead and try 17. I just like to try in the middle there. So again, I'm just getting an idea and trying some numbers. And in 17 years, my truck is worth $5,131. Okay, so it's still above the 5,000 mark. So let's try year 18. I have a feeling this is going to be it. Year 18, we get $4,643. So the value of my truck at $5,000 happens between year 17 and 18. In the 17th year, it is still above $5,000. In the 18th year, that's the first time it goes below. So use the graph or a table to predict when the value falls. Well, we don't know what year the truck was bought, so we know that after year 18, after 18 years, the truck value is below $5,000. So we know that it happens between years 17 and 18. So if we want to get more specific, we could start trying putting in 17.5, 17.25, or 75, and we could get a little more specific. So we're just getting an estimate here. So I would come over here at 5,000, and it would be down here. I'd find that that would be around year 18. To get a more accurate answer, again, we would set this equal to 5,000, and we would solve it using logarithms, which will be future lessons.